Consider this request. Explain why the sky looks blue in exactly 2 sentences for a 10-year-old. Here are 3 possible answers. Which one would you choose? A is correct, clear, and follows every instruction. B is correct, but too technical and too long. C uses the requested format, but its explanation is wrong. Suppose you choose A. This tells us which response you prefer, but not by how much. It also combines correctness, instruction following, and clarity into one judgment. Neural network training requires a numerical loss. So how do we turn this preference into a loss? Take the words, "the sky looks." In the training text, the next token is blue. The model assigns a probability to every possible next token, and the loss uses the probability it assigned to blue. A higher probability produces a smaller loss. A lower probability produces a larger loss. Training repeats this calculation at every position across an enormous amount of text. But the loss checks only how well the model predicted the text. It does not separately check whether a complete response answered the question, was true, or followed the requested 2-sentence format. For the sky question, a human writes answer A as the desired response. Training then increases the probability of the tokens in that response. Repeat this with many prompt and response examples, and the model learns to imitate patterns in those demonstrations. This stage is called Supervised Fine-Tuning, or SFT. But each demonstration provides only one target response. It does not directly compare 2 alternative answers or tell the model which one people would prefer. Instead of asking a human to write another response, show them 2 responses the model generated for the same prompt. Then ask which one they prefer. For the sky prompt, the rater selects A over B. When A is compared with C, the rater selects A again. We record 2 pairwise preference labels. A is preferred to B, and A is preferred to C. Repeating this process across many prompts creates a dataset of pairwise preferences. Each label records a choice between 2 specific responses. It does not assign either response an absolute quality score. Now train a second neural network called the reward model. It takes a prompt and one response as input and outputs a single score. For each labeled pair, training makes the chosen response receive a higher score than the rejected response. Suppose the reward model assigns A a score of 2, B a score of 0.5, and C a score of -1. These scores are not percentages or direct measurements of quality. To predict whether a rater will prefer A to B, subtract their scores. 2 minus 0.5 equals 1.5. Apply the sigmoid function to this difference, and the result is 0.818. The reward model therefore predicts an 81.8% probability that a rater will choose A over B. Only the score difference affects this prediction. Add 100 to every score, and the difference remains 1.5. The predicted probability remains unchanged. Individual reward scores have no fixed absolute meaning. The model learns to predict relative preferences within comparisons. Suppose the reward model initially gives B a higher score than A. Then the difference, A minus B, is negative, so the model predicts a probability below 50% that a rater will prefer A. But the recorded label says A was preferred, so the loss is large. Gradient descent updates the reward model's parameters to increase the difference between A's score and B's score. The predicted probability of choosing A rises and the loss falls. Repeating this update across the preference dataset trains the reward model to predict the recorded choices. This is supervised learning. Once training is complete, freeze the reward model's parameters. The next stage uses its scores to train the language model. A completed response receives 1 reward score. But the language model produced that response through many token choices. How can one final score train all of them? At each step, the model reads the prompt and the tokens generated so far. It assigns probabilities to the possible next tokens and samples won. After the response is complete, the reward model scores it. If the response receives a higher than expected reward, training increases the probability of each sampled token in its corresponding context. If the reward is lower than expected, those probabilities decrease. Repeating this process across many responses makes responses with higher predicted rewards more likely. In reinforcement learning terms, the prompt and generated text so far are the state. The sampled next token is the action. The language model's probability distribution over next tokens is the policy. The reward comes from a reward model trained on human preference labels. Sampling a response, scoring it, and updating the policy is reinforcement learning from human feedback, or RLHF. If the policy objective contained only predicted reward, assigning more probability to A would always improve the objective because A has the highest reward score. In this 3-response example, reward alone would assign all the probability to A. To limit this change, freeze a copy of the supervised model. This is the reference policy. KL divergence measures how much the current policy's response probabilities differ from the reference probabilities. Policy training maximizes predicted reward minus beta times this KL divergence. Now use the worked numbers. The reference assigns A, B, and C probabilities of 25, 50, and 25%. Their reward scores are 2.0, 0.5, and -1. With beta equal to 1, maximizing the combined objective gives probabilities of approximately 67, 30, and 3%. Why not assign everything to A? Increasing A beyond 67% continues to increase expected reward, but the KL penalty increases by more. The combined objective, therefore, decreases. The KL term does not determine whether a response is true or good. It only penalizes changes from the response distribution learned during supervised fine-tuning. A model may be capable of producing a helpful response while assigning that response a low probability. Post-training changes the response probabilities so that helpful instruction-following outputs are generated more often. This distinction explains one result from the InstructGPT study. On the prompts used in that study, human evaluators preferred outputs from a post-trained model with 1.3 billion parameters over outputs from the 175 billion parameter GPT-3 baseline. This result does not show that the smaller model had more knowledge or greater general capability. It shows that for those prompts and evaluation criteria, post-training made the smaller model produce responses that people preferred more often. A reward model is trained on a finite set of human comparisons from particular prompts and model responses. Policy training changes which responses the model generates. Eventually, the reward model must score responses that differ from those in its training data. Those scores can be inaccurate. If the reward model gives a poor response a high score, policy training increases the probability of that response because its objective uses the reward model's score, not an independent measure of response quality. Researchers can detect this mismatch with a separate evaluation that is not used for training. In controlled studies, the reward model score continued to increase as optimization increased. The separate evaluation improved at first, reached a maximum, and then declined. This is reward overoptimization. No intent to cheat is required. The policy is optimizing the objective it was given. The failure occurs because the learned reward model makes errors on some of the responses produced during optimization. Consider this request. The sky is blue because it reflects the ocean. Can you confirm? One response says, exactly. The ocean makes the sky appear blue. The other says, not quite. Air scatters blue light. The first response is false. The second is correct. But if the preference labels repeatedly favor agreement, the reward model can learn to give the first response a higher score. Policy training then increases its probability. This behavior is called sycophancy. The model agrees with the user's stated belief when correcting it would be more accurate. Give two raters the same prompt and the same two factually correct answers. The first answer is brief and blunt. The second is longer and more empathetic. Rater 1 is instructed to prioritize concision and chooses the first answer. Rater 2 is instructed to prioritize empathy and chooses the second. Both choices follow the instructions each rater received. So, human preference does not mean one judgment shared by everyone. Each label records what a particular rater chose between particular answers under particular instructions. These labels are used to train the reward model. Change the raters, the candidate answers, the instructions, or how their choices are combined, and the training labels can change. That changes what the reward model learns, and in turn, which behaviors policy training reinforces. Each human comparison trains the reward model to assign a higher score to the preferred response. The reward model then scores complete responses generated by the policy. Policy training makes higher scoring responses more likely, while the KL penalty limits the changes from the frozen reference policy. This is how a finite set of comparisons can guide changes across billions of policy parameters. RLHF makes human feedback scalable, but the policy optimizes a learned prediction of that feedback, not the human judgments themselves.